All right, everyone. So I'm giving you for your warm-up a complex circuit. You saw a little bit of a complex circuit when you did your reading worksheet. So I think it was 35-3 had some complex circuits at the very back. And you also have a complex circuit in your electric house. So I literally took the series circuit and the parallel circuit that is required for your electric house, and I put them into a diagram. And I want you to use your intuition to try to figure out how to find all these different values. We've never gone over complex circuits, so do the best that you can, and then we'll go over it together. And then I want to make sure that we get a little more practice with complex circuits, so I've decided to post, excuse me. I'm too nervous. Get over here. I postponed the test till Thursday, so you have a little more time to study. We'll do another warm-up on complex circuits, and I'm going to use Tuesday for a work day to work on the electric house project.
The quiz or the test?
What?
The quiz or the test?
Sorry, this is the test. I did the test. So this is your electricity test.
Was that like the last Thursday?
That's going to be, yeah, so I'm going to need to drink water in a minute. But that's going to be our last Thursday, and then we're going to have one more week before finals week. So that week I'm going to squeeze in just a little bit of magnetism, but probably not enough to do. You might have a quiz on it, but this is the last big test you're going to have. We're not going to have a final. You're going to focus on your project, and then maybe have a small quiz on magnetism, but maybe not. Question. Let's start with question number 1. It's a complex circuit, but if you're just looking at R1 and R2, you should notice right off the bat that they are in series with each other. They're along the same line, the same wire. And so if they're in series, you just add the two resistors together. That's in your physics helper. It's the concept of series circuits. So you get a total of 4. Are there any questions on that? Easy peasy, right? Question number 2 talks about R3 and R4, which is a parallel circuit. If you notice, they are next to each other. And if you were to follow the resistor or the light bulb, you would follow that wire right back to the battery. So I know I'm going around everyone's work, but each of those resistors, maybe it's not obvious right away, but it's directly connected to the battery in its own individual wire. So that's what makes it parallel, is that they have their own loop directly connected to the battery. And the equation for parallel resistors is to take the inverse of each of those resistance values, add them together, and then take the inverse of the answer. So 1/2 plus 1/2 equals 2/2. That equals 1, which is just 1 if you inverse it. And that's your total resistance through R3 and R4. Any questions on that? All right, good job so far. Voltage drop through R3 and R4. So if you look at this resistor, as I stated, they're in parallel. And if they're in parallel, they have a direct connection to the battery, which means that they are going to have all the voltage of the battery go through that resistor. So the voltage drop is going to be 6. Where is it? 6 volts through R3 and 6 volts through R4. And then if we're looking at the total voltage of R1 and R2, because it's saying the voltage drop through that whole series together, it's going to be a total of 6 volts. Because combined, they are directly connected to the battery. Any questions? Now, I'm going to talk about a vertical circuit because some of these concepts are a little more obvious if you can see it visually. But for now, everything is perfect. It's 6 volts through each resistor, and then, oh, I skipped number 4, and it's 6 volts through R1 and R2, or together.
So for R1 it would be 3 and R2 3.
Exactly. So this is how we get, so that's basically answering question number 6. But I skipped number 4. This one is asking for the total current through each resistor in parallel. And to do that, you would need to take the voltage drop, which we established was a total of 6 volts, and 1 ohm. Where did the 1 ohm? Oh, did you take the total current here? So the total resistance together is 1 ohm, which means that the current coming in is 6 amps. And then this group decided to split it up. And if 6 amps splits into 2 even currents, it's going to be 3 amps here and 3 amps here. So that's one strategy of solving it, and I like it. Perfect. So we got our current going through our parallel. We've got the voltage drop going along each part of our resistor. These are all 6 volts. And just like what Avery said, is that because this is 6 volts, and we know that R1 and R2 are equal resistance values, we can just split the 6 volts into 2 different resistors. Oops, that should be 3. And you just divide it and you get 3 volts each. So that's using proportional reasoning. The fact that the resistance is the same means the voltage drop is going to be the same. And if I have 6 volts total, it's got to be 3 and 3. Question?
For number 5,
Uh-huh.
I thought for voltage drop you did that's for voltage drop. Never mind. I think I just
So are there questions for anything so far from 6? Adele. We did, yeah. So the voltage drop through parallel resistors, because these are in parallel, it's going to be the same as the total voltage given by the battery. Basically, because they're directly connected to the battery, it's going to use up all the voltage. No, in parallel, it's always equal. 6 and 6. For series, it has to divide up the 6 between the 2 resistors. Any other questions? All right, so we're on 7. 7 is asking, what is 7 asking for? The current through R1 and 2. What we know about R1 and 2 is that they're in series. We also know that the current going through them for series circuits stays the same because there's only one wire going through it. So what we need to take is our total voltage, because current is voltage divided by resistance, and we're going to divide it by the total resistance, so total voltage divided by total resistance, and that gives us 3/2 or 1.5 amps. So for a series circuit, let me use a different color, the current is going to travel along the wire and it's going to stay the same. Whereas in a parallel circuit, it splits, the 6 amps coming in splits off into 3 and 3 as it splits the wire. Any questions on the current? Last but not least, the total current of the circuit is, we've got 1.5 coming in from the series, we've got 3 amps coming in from this parallel, and we've got 3 amps coming in from this parallel. Each of those branches, 3 amps, 3 amps, and 1.5 amps, because this is just one wire, add together to get your total current. 1.5 plus 3 plus 3 to get 7.5 amps. So that's the easiest way to do it. And I wanted to show you the vertical circuit version of this just because it's just another method. And obviously, you guys are able to figure it out. And if this makes sense to you, awesome. If it doesn't, I'm going to draw this as a vertical circuit, which means I'm just taking the positive side of my battery and I'm separating it from the negative side of my battery. So here's the negative, here's the positive. 2 ohms, 2 ohms, 2 ohms, and 2 ohms. Oops, I'm gonna write this on the other side. The reason why I like to do this is because the voltage drop, you can think about it as a vertical drop. Here I've got 6 volts, and if it's 6 volts all the way down to 0 volts here at the bottom, any of my circuits in parallel is going to start at 6 volts and drop down to 0 volts. Same here. You can visually see that there's only one resistor in that vertical line. Whereas here, we've got 2 resistors in series, which means that my voltage drop has to split. In total, it's going to be 6, but they have to break down into 2 different sections, which is 3 volts each. It only works out to be 3 volts because of the fact that the resistance is equal. So you might have to calculate it if these weren't 2 equal values. But visually, you can see that they should be even. And the current is pretty easy to see as you have a total current coming in. So this is my I total. And it splits off into what we established for the series was 1.5 amps. And then here it splits off into 3 amps and 3 amps. So you can visually see how the current kind of breaks off into different branches with different values. So the vertical circuit is another strategy that you can use. You can even include a VIR chart with that also. But it'll get you the same answers on what you did just through basic analysis. Any questions on this? So for your project, I want you to pull out your electric house project sheet because there's a section at the bottom under specifications that I want you to fill in. So it's a kind of tan or gold color. And on the back, it's left blank, but I want you to fill this in. Specifications And let me just grab a battery in the back. So the batteries we've been using in class have been 2 batteries end to end, and each of them is 1.5 volts. So this is a 3-volt battery if we put them together as 2. Now, if you are working maybe with a group of 3 and you decide you're going to use 6 light bulbs or 7 light bulbs, 2 of these batteries together might not be enough voltage to light up what you need. So you have the option of going to 6 volts in your circuit if you have more bulbs. It'll make your lights brighter with a higher voltage. Now, your resistance for every single bulb is 50 ohms, so that's something that you want to write down. 50. And you're going to use these values, whatever voltage you decide to use for your electric house, and however many bulbs you decide to use in whatever configuration you decide to use. You are supposed to create a blueprint evaluation on a poster board that walks us through the diagram of your circuit house, which I gave you the basic circuit up here. So this is what a basic parallel and series circuit looks like. But I also want you to include the predicted total resistance, the total current, the total power, and what you measure the current, voltage, and power to be. So show your calculations for that. This is a complex circuit. So we're going to do one more practice on complex circuits next class. And I'm going to give you work time next class to put together your electric house. But I would highly recommend that you start putting together your poster, and I can help you with some of these calculations. Okay? So I want to do one more practice with complex circuits. In your review worksheet, if you turn to the back page, you have 2 complex circuits at the very back. And we're going to work through 9B together. So this problem right here, I'm going to do with you. This is the harder of the 2, so I'll do this one with you. You do this one on your own. Okay, so we're going to turn this into a vertical circuit. So I'm going to start off with the positive side, and I'm going to notice my wire breaks off into 2 separate parts. So here's my positive. I've got 60 volts, and I'm going to break off into one section that has a 16 ohm and another section that has 2 10 ohm resistors. So I've spread out into this section and this section. After my 16 ohm resistor, I spread out into 2 more resistors in parallel, which are 8 and 8. I'm drawing it vertically. So basically, I'm taking the positive end and I'm working my way down to the negative end, but it's like I'm taking this negative end and I'm making it vertical down here. It's just a different way of looking at a circuit. Instead of making it closed, you draw it vertically, and you can kind of see voltage drops a little bit better that way. You can see current splitting a little bit better. So if you kind of follow my process here, I start off the positive, split out into 2 parts. I follow my 16 ohm. After that, I split off into two, and then it all comes back together at the bottom. So this is my negative side at 0 volts. This is my positive side at 60 volts. It doesn't change anything. It's just drawing it differently.
Is the 16 part of a parallel circuit with 10, or is that first 10 is series?
So these are parallel to each other. These are in series with each other. And then these are parallel to each other. So that's why we call it a complex circuit, because we've got a parallel, we've got some series, and then we've got a parallel again. But what we're going to do, I know this looks complicated. What we're going to end up doing, I wish I had more room than this. What we're going to end up doing here is we're going to simplify this circuit by redrawing it so that it doesn't have so many series and parallels entwined in it. So let's start with the most complicated part. I'm going to look at this parallel circuit right here. How do we calculate the total resistance or the equivalent resistance of this circuit? Just that section. What do I have to do? What type of circuit is it? Good.
Add 1/8 plus 1/8, and then you get total resistance.
2/8. Flip that around and you get 4, right? So my total resistance of that is 4 ohms. I'm going to take that and I'm going to redraw it. So now I've got a section that has 16. I'm going to redraw this parallel circuit, and instead I'm going to turn it into a 8 ohm circuit. So this is 16 ohms, this is 8 ohms, and then on the other side I'm going to keep it the same, 10 and 10.
Isn't it 4?
Oh, sorry, 4. That's our equivalent resistance of the 8 and 8 next to each other. Doesn't this look so much better? Good. Now we've got series, so we add them, and we've got series, and we just add them. Simplify that out. What do I get for the total resistance on each side? Very good. 20 ohms and 20 ohms. We ended up with a parallel circuit as we simplify it down. And my last and final step to get my total equivalent resistance, everything added together, is going to be what? How do I calculate this? I just add it? What do you think, David?
We're going to do 1/20 plus 1/20 plus 2/20.
And then flip that over and it's 10 ohms. So be very careful. This is not in series. This is in parallel, because notice how it splits and goes down to the opposite side of the battery. And if you look at it vertically, they literally look like they're parallel to each other, right? So we know that we're going to use the inverse equation, and I end up with a total resistance of 10 ohms. So that's what you're going to write in your worksheet. You're going to write R total. Sometimes we call it R equivalent. That's this. We started here, and we worked our way down to here. How would I calculate my total current? Now that we've got our total resistance, what do you think that total current would be for this complex circuit? Good. So I already know that my voltage is 60. And the voltage drop across my simplified circuit is going to be 60. So all I need to find is my total current traveling through here. And if I use my VIR equation or my VIR triangle, it's just voltage divided by resistance. So my total current is 60 divided by 10. Easy peasy, lemon squeezy. Maybe not easy peasy. Question. When you have it kind of circular in series. Yeah, so let's say if we had it, I'm just gonna turn this off so that we don't have too many images on my screen. So this would be a series circuit that's drawn normally, right?
Yeah.
So this is in a series circuit in one loop, but when you look at it vertically, you're gonna see that they're all in one line. And so it's just a different way of looking at it. Because if I just stretch this out, I took one side, positive side on top, negative side on the bottom, it would just make a line of resistors in series. For this one, so the fact that they're not one on top of each other along the same wire means that they're parallel because it's split into two separate wires. So this is what a vertical parallel circuit looks like. This is what a vertical series circuit looks like. If it confuses you, stick to just this. I just wanted to give you this option because for when I used to teach AP, my AP students had to solve a lot of complex circuits, and they found the vertical circuit to be super helpful. So if it's confusing to you, don't worry about it. Just make sure that using this still gets you the same answer as what the answer key tells you. All right? Any other questions?